So we're going to continue our discussion on gases and finish it up. And then we're going to get into energy afterwards. So we were talking about velocity in the last class and relating it to kinetic energy. And we have our root mean squared velocity, which is 3RT divided by our molar mass. So the square root of 3RT divided by molar mass. And we can use that to figure out our average velocities. Now remember, the bigger the molecule, what we see from this equation is the slower the velocity. But we also see from this equation that the higher the temperature, the faster our velocity. So just looking at those relationships, we get a lot from that equation. Also, when we're using this equation, we're using this gas constant, which is not the same or that we used in PV equals nRT. And that's really important to recognize when to use the correct constant. So, in order for everything to have the same kinetic energy, heavier molecules have to have a slower average speed. And that's what we see with our Boltzmann distributions. That, notice, again, because our average kinetic energy is all the same. As our molecule gets smaller, the speed is spread out a bit more. But overall, what we see is the smaller the gas, the slower, the faster it'll move. But notice that the distribution is, in fact, wider. And as our gas gets bigger, it's going to move slower. What we also see is the absolute temperature increases, the average velocity increases. So here we're looking at the same gas, presumably. And as we increase the temperature, again, the distribution does get bigger, but the overall velocity does get faster. So if I give you a distribution, I could ask you some things like which gas or which distribution represents the gas that's at the highest temperature, which distribution represents the gas that's bigger. So depending on what I'm asking. But you do get more of a spreading out, which means that if you pick any given molecule, some might be moving faster and some might be moving slower, but overall the average speed is faster. So we can calculate our root mean squared velocity if we know the molar mass or if we know the gas. So in this case, we're given the temperature, 25 degrees Celsius, and we're given what the gas is. In this case, it's methane gas, CH4. So we can calculate the molar mass. So to calculate our root mean squared velocity, we need our temperature to be in Kelvin because of what R is in R's units. So we need Kelvin. Pretty much every time we talk about temperature in this chapter, we must convert it to Kelvin. And then we can calculate our molar mass of CH4, which is 16.04 grams per mole. And of course, that would be from the periodic table, which, hey, look, we have some now. So we can point to those. There's also one back there. So when we're looking at that, we can think about our size there. So we can calculate our molar mass. So if we have our molar mass and we have our temperature, we can calculate our root mean squared velocity. So our U or MS is equal to the square root of 3 RT over molar mass. We have T, we have R, and we have molar mass. So our R is 8.314, and that is in kilograms times meters squared over seconds squared over mole K. So that's why we need that Kelvin. And our temperature, when we calculate that, is 25 degrees plus 273. So that's going to be 298 Kelvin. Well, 298.15. So our Kelvin cancels out. Now, here's the key. Our molar mass must be in kilograms per mole because R is in kilograms. So because of that, that is the one trick with this. But if you follow your units, you really don't have to memorize that. So for kilograms to cancel out, our molar mass has to be in kilograms per mole instead of grams per mole. So 16.04 grams per mole would be equal to 0.01604 kilograms per mole. Remember, there's 1,000 grams in 1 kilogram. Kilograms bigger. So we do have to do that small conversion because of what our R is in, our units. That way, kilograms and moles can cancel out. So, of course, that gives us our URMS in meters per second, which makes sense because that is a measurement of velocity. So this is meters squared per second squared, but we take the square root, so that gives us meters per second. So following your units, you really don't have to memorize that the molar mass has to be in kilograms per mole. It has to be so those kilograms cancel out. So that's our root mean squared velocity of methane gas at 25 degrees Celsius. Now, of course, at a higher temperature, that would be a faster root mean squared velocity, and at a lower temperature, it would be a slower root mean squared velocity. So looking at this one, we have a gas sample A that has a molar mass 3 times that of another gas B. So first off, the smaller gas is going to move faster. So that's B, because A is 3 times the molar mass. So our answer is either going to be C or B. But it's 3 times the size of the molar mass, so that means that it's going to be the square root of 3, because that molar mass is going to be 3 times the size. So it's actually going to be 1.7 times faster. But I will give some partial credit to D, because B is a smaller gas, so you should be able to figure out that B is going to be faster. The next thing we're going to talk about is diffusion and effusion and what those terms mean. So our molecules in a gas, they pretty much travel in a straight line until they hit something, either another gas or the container. So the average distance a molecule travels before a collision occurs is what we call our mean free path. And of course, the more space, meaning the less gas molecules or the bigger the volume, the mean free path will typically be longer because there's less of a probability it's going to hit something else. So as our pressure increases, our mean free path is going to decrease, because that means that there's a higher probability that our gas molecule is going to hit something before it goes off of its straight path. And that makes sense, because the whole reason why we have a higher pressure is because our gas is hitting either the side of the container or other gas molecules more. So if we have a lower volume, so we have a higher pressure, or if we have more gas molecules, we'll have less space to move and our mean free path will decrease. When we're looking at diffusion and effusion, if we have a box that has a high pressure of gas molecules, the process of collection of molecules spreading out from high concentration to low concentration is diffusion. And we always diffuse from high concentration to low. If you're always surrounded by air, but you have air trapped in your tire. If you get a hole in your tire, what's going to happen? The air is going to go out of your high pressure tire and into much less pressure, which is the air. So we always get that diffusion. If we're getting a collection of molecules through a small hole in a vacuum, that's called effusion. So there we have to have a vacuum present. Both the rates of diffusion and effusion of a gas are related to our root mean square velocity. How fast the gas is moving is going to affect how fast or our rates of diffusion or effusion. So for gases at the same temperature, the rate of a gas movement is inversely proportional to the root mean square of their molar mass, or proportional to the square root of their molar mass. So that's what we're seeing there. And again, remember, temperature means the gases will move more. So this is dependent that we have the same temperature if we're describing the diffusion rate of two different gases. So if we look at this one, which is true about diffusion, diffusion is the process of a gas molecule spread out in response to a concentration gradient. Generally, lighter molecules are going to have a faster rate, so therefore they're going to diffuse faster than heavier ones. So that's usually what we see. And then A and B are pretty much saying the same wrong thing. They're both saying the same thing, just both wrong. So it makes sense that if we're comparing two gases, the higher molar mass gas is going to diffuse or effuse slower because it's not moving as fast. So that just makes sense. So based on this, Graham's law of diffusion is for two different gases at the same temperature, the ratio of their rates of diffusion is given by this equation. Rate of gas A divided by rate of gas B is equal to the square root of the molar mass of B over the molar mass of A. And then we can get the rate that A will diffuse either faster or slower than B. If gas A is a heavier gas, then that number is going to be less than 1. If gas A is lighter gas, then that number will be greater than 1, because a lighter gas will diffuse faster. So this is what we can use to figure that out. So if we look at this one, we want to calculate the molar mass of a gas that diffuses as a rate 0.462 times N2. So that means, and again, this is a ratio. This isn't telling us the exact velocity it's diffusing. This is telling us the ratio of one gas diffusing versus the other. So that's important. Notice that our this is a ratio, so it's dimensionless. There's no units attached to this number because it's not the actual rate of diffusion of the gas. It's just giving us a ratio of the two gases. So the first thing I should note is because this number is smaller than 1, then the gas is likely going to have a higher molar mass than N2, meaning it's going to be slower. So that's one thing that we can kind of get from this equation. So we can calculate this because we know the molar mass of N2, or we can calculate the molar mass of N2, and we know our diffusion rate. So what this number is our rate of our unknown gas divided by rate of N is equal to 0.462. So that's what that tells us that number is. And then our equation tells us that rate of gas A, which is our unknown, divided by rate of N2 is going to be equal to the square root of the molar mass of N2 over molar mass of A. So we are looking for molar mass of A. We don't need to know what the rate of gas A is or the rate of gas B is because we know that overall this term is 0.462. So we know 0.462, which is our ratio, is equal to the square root. Don't forget that square root is important. Of our molar mass of N2 over our molar mass of our unknown. So I'm going to put that as X because I don't know what it is. So N2 is 28.01 grams per mole. And we don't know what X is, but that's what we're looking for. So we can solve for X. Again, bringing in a little bit of algebra for solving for this equation. We can take both sides of the equation and square it to get rid of that square root sign. And that's going to give us 28.01 grams per mole over X. Bless you. So when we solve for this, I can multiply both sides by X so it cancels out. And when I solve for X, I get 131 grams per mole. And that makes sense. What that tells us is N2 is smaller, so it's going to have a faster rate. So that's why that number is less than 1. And of course, I can figure out what the unknown gas is if I can find a gas that has molar mass close to that. One more example of this. I want to know the ratio of a rate of fusion for oxygen versus hydrogen. So in this case, I'm comparing oxygen and hydrogen. Oxygen is going to be bigger. It has a larger molar mass. So I know that that number is going to be less than 1. Now, if I was comparing hydrogen to oxygen, that number would be greater than 1. So it's about what this question's asking and what I'm comparing with. Because this is just a ratio of one versus the other. So make sure that you're reading what the question is asking you to calculate. Now, we're not actually going to find the rate of each. We need a little bit more information to do that. If we knew the rate of one, then we could find the rate of the other. So we're looking for our ratio of the rate of oxygen to the rate of hydrogen gas. We have our molar masses. We can calculate those from the periodic table. So all we have to do is plug that in. Our molar mass of H2 goes at the top, and our molar mass of O2 at the bottom. I don't know why I just put a 1. Notice grams per mole cancel out. That makes sense because, again, this is a ratio, so it's unitless. So our answer is our ratio is going to be that H2 is moving faster than O2, so that makes sense that our ratio is less than 1. This is it for the gas chapter. Now we're going to start talking about energy. Oh, and answering this one. Oh, we're not quite done. We're going to talk a little bit about conditions. So we've mostly been talking about gases behaving under more ideal conditions. But let's talk about what happens in extreme conditions. So conditions that aren't ideal. So we've been talking about pretty ideal conditions. Of course, our most ideal conditions is our standard temperature pressure. But most of what we're doing in the lab is going to be pretty ideal. But what happens in extreme conditions? So real gases often might not behave like ideal gases, especially at extreme conditions of high pressure or low temperature. And those are going to affect how the gas typically behaves. So we know our molar volume for our ideal gas is 22.4, and that's pretty much true at those ideal conditions. But our ideal gas law assumes no attractions between gas molecules, and the gas molecules don't really take up space based on kinetic molecule theory. So that's pretty much true at our ideal conditions. We know our gas molecules, we consider it negligible that they are interacting with each other. And also that they're pretty small, so they're not really taking up space themselves. What takes up space, what changes the volume, is the gas hitting the size of the container. And any size container, put the gas in, it'll fill. So that's our typical conditions. But at low temperatures and high pressures, these assumptions are not valid. So we're going to look at those two examples and what's not valid based on those. So because real molecules do take up space, the molar volume of a real gas is larger than predicted at high pressure. So really what's happening is you've gotten to the point where you are closing the volume so much that now the size of the individual gases make a difference. So typically we have so much extra space that the actual size of the individual gas molecules don't make a difference. But at really, really high pressure, they do. So the amount of space occupied by the molecule is significant amount of total volume, whereas under normal conditions, that's not true. So you can see that really starting to take shape and seeing that change at very, very high pressure. Now remember, ideal temperature pressure is 1 atm. So what we're looking at here, 1,000 atm, is very, very high pressure system. But you see it even as low as 400 atm, it changing from our ideal conditions. Though that's not typically a relevant pressure. Even often if we're trying to force organic or reactions to occur, we won't really use more than 200 atm. Because this is a lot of pressure when we're talking about 400 atm. So we have a significant amount of volume that the gas is taking up. And therefore, it's not going to behave under our ideal gas law. So there is an equation. You don't have to memorize this. I won't have you do it. But there is an equation, van der Waals equation, and it's only relevant under those high pressures. But it takes into account the size of the gas. So then we have a second in for our moles, and then a second constant, which is van der Waals constant for that particular reaction. So that takes into account that difference. Also, real molecules can attract each other, especially when we're talking about really low temperatures. Remember, at low temperatures, our gases aren't going to be moving very much. So since our gases aren't moving very much, they're typically going to be attracted to each other more. Usually at normal conditions, our gases are constantly moving, so their attractions between each other is negligible. But now it's going to matter, and we can see that as we get closer to absolute zero, we see that change from ideal behavior. This is being represented with xenon. So it becomes more significant because the gases aren't moving. And then there's another equation. Again, you don't have to memorize this. I just want you to understand how the gases behave when we're not talking about typical conditions, but extreme conditions. So A is van der Waals constant, and it's different for every gas because their molecules have different strengths of attractions. And we'll talk a little bit about some of those intermolecular attraction forces in chapter 8 and 9. So we'll look at what those forces come from, but right now just recognize that A would have to be different for every gas because of the different strengths of attraction. Combining those two equations, we get this total equation for real gases at those extreme conditions. So that just has both of those constants in. Again, not something I'm going to make you actually calculate. I just want you to understand how gases behave at non-ideal conditions. So CO2 would be least ideal under high pressure and very low temperature. So that's it for gases. Now we're going to get into thermal chemistry which is going to be the study of energy in chemical reactions. But first we got to understand energy. Typically when we hear the term thermal, we're typically talking about heat energy, but we're also going to be discussing kinetic energy and besides just heat. But that's what we're typically thinking about when we talk about thermochemistry. So we're going to get a little bit into endothermic and exothermic reactions, and also endergonic and exergonic reactions, and the difference between that terminology. But first we got to talk a little bit about energy. So of course we use fossil fuels to generate heat. We use that all the time. And the temperature that you are increasing the inside, which is not happening in this room right now because it's freezing, is relevant to how much fuel is burned, the volume of the house, of course, the amount of heat loss, how well is your house insulated, the efficiency of the burning process, different fuels burn differently, and there's a lot of other things that go into it. So we're going to be applying this concept of energy and heat to chemical reactions. So even though chemistry is a study of matter, energy affects matter. So energy is really important to the study of chemistry. Energy is anything that has the capacity to do work, and work is a force acting over a distance. So energy is equal to work, and work is equal to force times distance. Now energy can be exchanged through objects or collisions. So you're standing right here, but I can move you. So I'm applying energy to you, transferring that. Now you have to say that. So energy can be exchanged through contact and through collisions. You can think of energy as a quantity an object can possess or a collection of objects can possess. You can think of heat and work as two different ways that an object can exchange energy with other objects, meaning putting out energy, taking energy into it. And we're going to be looking at heat and work and how that all applies. So kinetic energy is the energy of motion or energy that's being transferred. So thermal energy, when we're talking about heat, is a form of kinetic energy. That could be energy due to motion. And then motion, heat hits something that's stationary, which transfers the energy, and then the thing that was stationary can now move, so that energy can be transferred. Potential energy is the energy that is stored in an object or energy associated with composition or the position of the object. For example, if I'm holding up a pool ball and I let it go, the gravitational pull is causing the potential energy that has before it starts falling. We're going to really be thinking about potential energy when we're thinking about chemicals. So if we say that a compound is reactive, it has a lot of potential energy because it's starting off higher energy. And in most cases, compounds, reactions, or elements want to exist in their most stable form, which is why something like sodium metal is so reactive, because it's unstable in its elemental form. It has a lot of potential energy. And therefore, when it reacts, it releases a lot of energy, which is why if I put sodium metal in water, it catches on fire, because it releases so much energy when it reacts. And we're going to be talking about why it's unstable in later chapters. But in this chapter, we're relating the concept of this to energy. There's a couple of different types of energy. There's electrical energy that has to do with the flow of electrical charge, which of course is electrons. Heat or thermal energy, associated mostly with molecular motion, and we'll be looking at that thermal energy a lot in this chapter. Light or radiant energy, that's our kinetic energy associated with energy transitions in an atom. We won't be looking at that so much in this chapter. Later on in 106, you're going to be looking a bit more at that. That's where the fact that if we put something like UV radiation to a molecule, that can excite an electron from one energy level to another. And when the electron relaxes back down, it releases energy. So we won't really be looking at that right now, though we will be in chapter 7, sort of looking a little bit at mapping out electrons, electron configuration, and quantum numbers, but we won't be applying light to it just yet. So we won't be looking at that. Nuclear energy is the potential energy in the nucleus of atoms. That makes sense. And then chemical energy is our potential energy due to our structure of our atoms. So a chemist will be able to not only understand heat and thermal energy associated reactions, but also be able to look at a chemical compound and assess the potential energy due to the stability or instability of the chemical structure. And you're going to get there. Organic chemistry is really the study of looking at organic compounds through being able to do this. So it's definitely something we're going to work up to. Right now we're going to be mostly focusing on heat and thermal energy and the transfer of energy in chemical reactions. But we will discuss a little bit about chemical energy and potential energy of compounds. So, of course, energy cannot be created or destroyed. Energy can be exchanged, however, between objects. So energy can also be transformed. Heat energy can be transformed to light energy, to sound energy. There's a couple of ways we can transform energy, but it's not being created or destroyed. It can be transferred. And our most common that we'll be talking about is transferring potential to things like kinetic energy or thermal energy for this particular chapter. So we're going to be talking a lot about chemical reactions. And our chemical reactions are typically going to be our system. And then what happens outside of our system is our surroundings. So because energy can be created or destroyed, it can be either taken in by a system or released by a system. So we define a system as the material or process that contains the energy changes we're studying. And we define the surroundings as everything else in the universe. Now that's not going to be really useful to calculations. So typically what we'll do when we're trying to study the transfer of energy is our system is going to be our reaction, and our surroundings is going to be a controlled set of surroundings where we can measure the change in energy. So we might, for example, look at the increase in temperature of the water part of our solution, which is our solvent, because then our chemical reaction is our system and the solvent is our surroundings. So we're going to have to define it more specifically, just that way that we can actually have a controlled system that we're following. So energy can be taken from the system and put into the surroundings, or the system may be taking energy from the surroundings. And again, we'll mostly be talking about a change in temperature, but there's other changes that can be affected as well. Some units, we've already looked at a little bit of units of energy. The amount of kinetic energy is directly proportional to its mass and velocity. So KE is equal to 1/2 mass times velocity squared. Meaning that the size and the velocity affect our kinetic energy. When the mass is in kilograms and velocity is in meters per second, the unit of kinetic energy is kilograms times meters squared per second squared, or a joule. So you're more likely is going to see the J, which is a joule, and you need to recognize that 1 joule equals 1 kilograms times meters squared over second squared. And we use that in our root mean squared velocity because that was a measurement of energy. And again, notice that we have kilograms, meters, and seconds. So that's going to be important when we are working with units. So following your units is a great way to make sure that everything's in the correct units that you're working with. So you'll see joules a lot, but you should recognize this conversion. 1 joule is the amount of energy needed to move 1 kilogram mass a distance of 1 meters. So again, that's your kilograms times meters squared over second squared. And joule is your SI unit for energy. Now you might see calorie. And a quick note, calorie is not the same as a food calorie. They are related, but they're not the same. So first off, a calorie is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. So a kilocalorie is energy needed to raise 1,000 grams of water by 1 degree Celsius. And when you're talking about a food calorie, you're really talking about kilocalories. I know, but that's how it is. So a food calorie is really a kilocalorie. But they are related. But as I said, mostly we'll be using joules and not calories as much. So here's some energy conversions. Again, you don't need to memorize these. I will give them to you. Though, I mean, you should be able to convert a calorie to a kilocalorie. If I want something to be a food calorie, I'll be very specific that it's a food calorie, because it is actually a kilocalorie. You might also see kilowatt per hour, especially when you're talking about machinery, things like that. But joule is the SI unit, so that's what we'll be seeing a lot more in our chemical reactions. So the first law of thermodynamics, the law of conservation of energy, the total energy of the universe is constant. When energy is exchanged between objects or transformed into one form to another form, all the energy total is still there. So the total amount of energy in the universe before and after the change are equal. We can't design a system that will continue to produce energy without some source of energy being put in it. When we're talking about combustion, you're like, well, we're producing energy in combustion. Yes, by burning fuel. It didn't come from nowhere. That came from a chemical reaction. So something can produce heat, but it produces heat from the transfer of other energy. So that's key. We're not actually producing something without nothing. So our change in energy, and then when you see from now on the delta sign, there's two ways that we use the delta sign in chemistry. One is meaning heat when we're talking about a chemical reaction over a reaction arrow. But in this case, in mathematical terms, delta is describing the change. So the overall delta energy of the universe is zero because we have a zero change in energy. So that's our overall change in energy of the universe. It has to be zero because energy doesn't change. It's not created or destroyed. So our change in energy of our system and our change in energy of our surroundings have to equal but be opposite. So if my system gives off 20 joules of heat, my surroundings is taking in 20 joules of heat. So my change in energy of my system plus my change in energy of surroundings are going to be equal but opposite signs, and overall they're going to be equal to zero. So if you know, because it's going to be really hard to measure our system, but we can measure our surroundings really easily. So it's hard to measure how much heat is actually being lost by our system, but we can measure how much heat our surroundings is gaining very easily. So we can figure out our system that way. And again, matter can't be created or destroyed. So whatever is happening to our system, the equal but opposite thing is happening to our surroundings. And again, delta just means change. That's just our final amount minus our initial amount. And when you see delta in terms of math, that's what we're looking at. Internal energy is the total amount of kinetic and potential energy a system possesses. The change in internal energy of a system depends only on the amount of energy in the system at the beginning and end. So not on anything else, because we're talking about just the energy of our system. So that's a state function. It's a mathematical function whose result depends only on the initial and final conditions, not on the process used. This might seem confusing, but I'm going to give you an analogy that really makes sense. So our delta E is going to be equal to E final minus E initial. So if we're talking about our change in energy of a reaction, that's going to be our energy of our products minus our energy of our reactions. But it doesn't matter how the reaction got there. And that's going to be really important, especially when you get to something like organic chemistry. So later on, we're really going to be mapping this out. So how does a state function? Let me give you an analogy that makes a lot more sense. If you're hiking up a mountain, let's say that there's two different trails you can take, path A, which is 12 miles, and path B, which is 5. But they both start at the same elevation, and they both end at the same elevation. So even though path A took you probably longer, and it's more miles, your overall change in elevation doesn't matter, because path A and path B both started and ended at the same place. So that's what a state function is. Your change in elevation, the height of the mountain, is a state function. The height of the mountain is not changing based on which path you take, but the amount of walking you have to do can change. How you get there changes, but overall the height doesn't. So that's what we're going to see with our energy when we're talking about that as a state function. And again, relating that to our reactions, our energy of our products minus our energy of our reactions is going to give us our total energy of the reaction. Energy diagrams are a graphical way of showing the direction energy flows in a process. So if we look at this, if our initial energy, and energy diagrams are always written where our lowest energy is here and energy increases going up. When we're mapping out the energy of a reaction, we can actually quantitatively figure out the numbers, but we don't have to, because we can do this comparison without actually seeing any numbers. So whenever we're doing this, it's really important that our energy increases. And later on, when we're going to be looking at our electron configuration diagram of our atoms, we're going to still be using the same concept, where outer orbitals are higher in potential energy. So this is typically relating that potential energy. So in this case, we're showing our initial and final. And in this case, I'm showing that my final energy is higher in energy. So in this case, my delta E, my change in energy, is going to be positive, because I increased in energy from initial to final. If we look at this example, my final energy is lower than energy than my initial. So in this case, my change in energy is going to be negative. Now, often you might think that negative is a bad term and positive is a good term, but that's not how we're thinking about this. We're just thinking about a change in energy, not whether overall good or bad. Now, as we look at chemical reactions, we're going to see that for a chemical reaction to occur, our product has to be lower in energy than our starting material. So usually we think of negative as bad, but that's not what we're saying here. We're looking at the change in energy. So when energy flows out of a system, it has to flow into the surroundings. So if we know just a little bit about what's happening, let's see whether the surroundings increased in energy, then we can figure out what the system did. Because whatever the system does, the surroundings have to do equal and opposite. So in this case, our delta E of our system is going to be negative because it's losing energy. But our delta E of our surroundings is going to be positive because it's gaining energy. So that's what we're seeing with this. So when energy flows out of a system, our delta E of our system is going to be negative. It's going to have less energy at the end of the whatever occurred. Whether we're talking about a chemical reaction or a transformation or whatever we're talking about, we're going to be relating this to chemical reactions, but this is a true concept whether we're talking about a chemical reaction or not. And when energy flows into the surroundings, so therefore our surroundings is positive. And as far as the magnitude, they're going to be equal. If this was negative 20 joules, this is going to be positive 20 joules, because our system is getting the energy, or losing the same amount of energy the surroundings is getting. So therefore our delta E system is negative and our surroundings are positive. The opposite system, where our surroundings is giving energy into our system, then our surroundings is negative and our change in energy of our system is positive. So then energy is flowing into the system and our system is overall positive. So therefore our delta E system is equal to negative delta E surroundings. And again, that magnitude is going to be the same. So when we are relating this to a chemical reaction, if we look at the total amount of energy, so there's a couple of things when we're relating this to a chemical reaction. We're usually going to compare the energy of our reactants and our products. But that energy level is the total amount of energy of all of our reactants and the total amount of energy of all of our products. So let's say I'm reacting something with sodium metal. Well, our energy of our system, of our starting material, is dependent on sodium metal plus whatever is receiving its electron. So sodium metal is really reactive, and we might just think about that fact, but our actual starting energy is based on both of those, whatever sodium metal is reacting with. So the total hot internal energy in 1 mole of carbon solid and 1 mole of oxygen is greater than the internal energy of 1 mole of CO2. Or we can think about it as the fact that CO2 is much more stable than elemental carbon and elemental oxygen are on their own. So that's how we often will equilibrate this in our chemical reactions. So that means that at the same temperature and pressure, of course, we would have to have everything in our system be at the same temperature and pressure. So if our reaction is we're reacting carbon with oxygen gas to form CO2, then because CO2 is lower in energy, our system's going to lose energy, and therefore our surroundings are going to accept them, because CO2 is lower than energy than our starting materials. If the reaction is the opposite reaction, so we're breaking up CO2 to form carbon, solid, and oxygen, well then we would have to increase in energy for our system because our products in this case would be higher in energy. That would be a really hard reaction to do because it's not very stable to reform carbon and oxygen. We're going to go back and map out things with chemical reactions and what we look at with these types of diagrams. And we're going to be looking at these types of diagrams a lot, and we're going to call them reaction coordinate diagrams, where we're basically following the difference in the starting material energy and our final product energy. And we're going to talk about which reactions are more likely to occur. But right now, let's focus on actual energy for a while before we get to that. So some energy exchange. Heat is our thermal energy, and it's typically represented by Q. So if Q is positive, the system's gaining heat energy. If Q is negative, then it's releasing heat energy. Now remember, if you are performing a chemical reaction and you're holding the flask and the flask is hot, that means that your system is what? Gaining or losing heat? Losing, because you're feeling the surroundings. So remember, we're going to be mostly equilibrating this to the surroundings because it's really hard to directly measure our system. So instead, we're going to be considering our surroundings. Now, our total energy difference also is attributed to not just heat, but also work. So system gains energy from work, it's going to be positive. If some system releases energy from work, from doing work, it'll be negative. So work is W. And of course, our delta E is related to that. So let's actually think about this. So let's look at our energy exchange. So energy is always going to be exchanged between system and surroundings. We just looked at that. Through either heat exchange or work being done. So on a smooth table, most kinetic energy is transferred from the first ball to the second ball as work, with a small amount lost through friction, meaning heat. So on a rough table, however, there's going to be a lot more friction from the ball with the rough table. So most of the kinetic energy is lost through friction, heat, and less is transferred to the second. So heat and work are related. So our delta E of the white ball in the example before is the same for both cases if it's moving the same. But Q and W are not the same. On the rougher table, heat loss Q is greater, so Q is going to be a more negative number. But on a rougher table, less kinetic energy is transferred, so W is going to be a less negative number. Again, Q plus W is going to be equal to the same for both systems. Delta E is a state function. It depends only on the velocity of the white ball before and after collision. But Q and work are dependent on your system. So that's really important. Overall, delta E is the same for both tables, but the actual value of Q and W are different based on what the system is. So Q and W are not state functions. Delta E is a state function. So if we look at this one, a system gains thermal energy, but does work against an external pressure. So it's gaining thermal energy. Q is thermal. It's gaining it, so Q is going to be positive, but it's doing work. Work is W, so it's losing that energy. Work is going to be negative. This doesn't tell you the magnitude of Q and work. It just tells you the sign. So when you're reading these examples on your own, it's going to be really important that you read what the question is telling you to figure out the sign of Q and W. And think about whether it's giving or losing. So these examples is just adding and subtracting. Delta E is just Q plus W. But the key here is to understand the signs of Q and W when you're looking at trying to figure out these. So let's go through one example in the last 3 minutes of class. Last 2 minutes of class, we'll just go over these examples at home and we'll work through them in the next class. And really read your question because it makes a difference whether Q and W is plus or minus. You guys have a great day. Oh, we're going to go over it in the next class. The answer is B, but we're going to work through it in the next class.